do something. I need core engineering students. Okay, now we can go forward. One second. Switch does. Now what? We talked about full start connection and zero sequence current. In distribution networks, distribution kind of networks, where isolated neutral is adopted, this thing was used. Okay, is A phase, B, C phase, transformer for A phase, transformer for C phase, and it's not aesthetic. I need to draw aesthetic schematics. E and relay for C phase. This one, incomplete star, or two relay star. This thing popular for 10 or 11 kilovolt networks, for isolated neutral networks. Two transformers, two relays. Idea in early days, these transformers were quite expensive, and at first glance, let's take a look. Schematics coefficient. Fault. What? No, it will be stupid table. Type of fault. Schematics coefficient. AB. What will be schematics? Ratio between transformer current and relay current. 1 BC, 1 AC, 1 and 1, both relay trip ABC, 1 and 1, no problem. Appears what this thing is usable. But something wrong. Really, in case of isolated neutral network, this works, no? In any possible fault, for ground fault, anyway we need zero sequence relay with zero sequence transformer. Where's the problem? Can we use it? Okay, it's not good for Earth at neutral because big ground fault is not protected. But for isolate neutral, what's the problem? Who can point finger? Problem. No? Yes, let's say my 10 kilo distribution network, 110. I can have here two transformer, this incomplete star schematics until if I have a cheap network. It will have cheap transformers. At the day money comes in, ungrounded star, grounded star transformer, very old regulation require put a cap 1.4.5 MVA. If higher capacity can be used, for higher capacity can be used. But problem, this cheap transformer is cheaper, but in case of asymmetrical load, customer will suffer from voltage and non-symmetry. Here is a different thing. 0.4 kilovolts. But where the dock is digging? It's net fault, everything okay. But here, for typical transformer, it will be BC fault. You will see something like this. Small a, long b, and small c. Remember my lectures from previous semester? I simulated this fault. And here on primary side, what we saw? One big and two small. Here we will have schematics factor 1/2. Incomplete star is not usable if we have bit expensive delta star transformers, because fault on the customer side will appear with schematics factor 1/2. Ouch! That's not good. That's not good. What can we do? What is this current? It's vectorial sum, whatever I think. It's a vectorial A plus C, yeah? But we have isolated neutral. E0 approximately 0. So, EA plus IB plus IC approximately 0. So this current is approximate minus B phase current. plant one more relays in return via of incomplete. This will sit on minus b. For this, schematic factor will be 1. Problem can be solved if you add a current sensing channel to the ground wire. This old, usually, this thing will, how to say, fall on you when you start to work on something old, maybe built till 70s. And you see one, actually maybe late. Such kind of transformer may appear even in 80s. And problem, you have two large transformers, current transformers, and B, or in your case blue phase, going between them. If you put third transformer, there will be no space. One of the problems with these old switchgears was they had no space for third transformer. Transformer, bus transformer. There is no room for third transformer, for middle phase transformer. It appears ridiculous, but in large serial manufacture distribution, they will look like steel bars. In case of modular, one transformer, 10, 12 connection, and you need to add one more column row to your building. Oops! Simple, because such kind of transformers take space. Transformer, bus transformer, everything okay. At the moment you wish to put a third transformer in middle phase, you don't have a space. Later started to use, because late digital relays do not require such power capacity from transformers, started to use smaller transformers. For smaller transformer, it is possible to fit smaller transformer, but on standard construction scheme, it's ridiculous, but there was no space for third transformer. Okay, one more. A greedy guy. Schematics. Current here is vectorial difference. Somewhere here should be grounding. Vectorial difference of currents. Current difference schematic. Here, very popular on 6.3. It's factories nets power supply, but you can find it in GE manufactured equipment, old GE manufactured equipment. You can find it anywhere. It can fall on you. What's good and what's bad? Nothing to do. We need to analyze. schematics factor. AB. What will be schematics factor? 1. BC 1. AC, and it will be 2. Difference, vectorial difference. ABC, square root from 3. First problem with it, schematics factor variance. That means what trade current should vary. Its problem is calculating trade current, but that's not all. Fold transformer. What will be? Lowest schematics factor. If we have 1, 2, if this is A, this is C, and long one is B. Yellow. Painted yellow. What will be schematics factor? This minus this equals to bold 0. Unusable. If you have transformers, delta star. This thing simple, unusable. If you unlock, old factory becomes a trade mall. Power equipment remains. Transformers 6.3 to 0.4. Switchgear old with 1 relay and 2 transformer. Everything fine until you decide, not you decide. Old transformers were oil field. At the moment you're building a trade mall, you need dry transformers because of safety regulation. Okay, you can go with fire resistant wall. But if you put new transformers, delta star, instead of all star, not grounded, star grounded, you're in trouble because your protection will fail. Okay, more. One more. Transformer connection schematics. It's a delta. Where X one, two, and 3. Strange thing, isn't it? First, it has schematics factors square root of 3, and this schematics is immune to ground fault. This thing will never trip at ground fault. It's appears to be strange, and why should I use it? Immune to ground fault. This kind of connection for overcurrent protection would be a BTV, I see an error. This should go here. For overcurrent protection it's quite strange. Why should I connect transformers in delta? This type of connection was used in differential protection and still used. Problem: you have a large transformer, for example, okay, let it be grounded start delta. You would like to implement protection based on Kirchhoff current law. As in flows, this out flows. So you need delta E, you need primary side current and secondary side current. Yeah, everything fine. Except one problem. It will be something like this. A phase at a start, if it's European, you will have 30 degrees here. It's a delta. Because it's a delta star transformer. You will see 30-degree shift. And this shift limits sensitivity of your protection. It's a problem. Old way to solve this problem with offset current transformer connection. Idea: if you have star here on primary side, A, B, C. Use delta as offset to start. And on the delta side, use star connection. This will compensate phase shift of transformer. For such purpose, transformers on it's for megawatt, maybe even gigawatt class power transformer for protection can be used or group of primary transformer delta connected, or very often it will be group of interim transformers. It was standard for many years to use group of interim transformer first to compensate phase shift introduced by connection scheme of main transformer, and second to compensate transformer rate of the primary transformer. Okay, when we will speak on differential protection, I will explain this deeper. But delta connection of current transformer can be used to compensate phase shift introduced by connection scheme star delta of the main transformer. Also, it's a very rare trick to make this protection immune to ground fault. There can be problem. For example, you have transformer head, yeah? It's grounded. If, for example, you have a fault, ground fault, on some different line, where zero sequence will go? Okay, you will see ground current flowing into center of neutral and going to fault place, or zero sequence flowing. It's an outer fault. Problem, transformer protection will see current inflowing but nothing outflowing. There will be imbalance and may trip falsely. To prevent it, you need or check for zeros, or this wire you may plan current transformer here. You may check for zero sequence, but one of the tricks, it's an old school. Use this delta connection, it will not pass zero sequence current through it. So, transformer protection will be immune to outer ground fault. Also to induce it's, how to say, from a rare thing, but if you have line, parallel lines, they are close, so they have M coupling, magnetic coupling. Ground fault here to magnetic coupling causes zero sequence current in this line. If lines are very close, then it can be problem. Delta connected transformers prevent influence from magnetic coupling. Usually it's done differently. It's done by controlling zero sequence current of parallel line, but one of them, it's exotic, but it can be. What here we have delta connection to make protection of this line immune to faults on parallel line. Okay. Next, tricks. Current transformer can be connected in series. Such connection doubles load capacity. If you connect current transformers in series, this will double load capacity of transformer. You can connect current transformers in parallel. It gives virtually no effect. It will bring small decrease in errors. Parallel connection yields no effect. Series connection doubles load capacity. Good transformers, good high voltage switch come with its built-in set of current transformer. Next time you drive near large power transformer, take a closer look on a place where high voltage insulator goes into main body, main vessel. You'll see it's kind of adapter, usually large cylindrical part, adapter between insulator and transformer body itself. If you open it, you can find 3, 4, even sometimes even 6 current transformers inside. Flat like donuts. So if you work, you will have spare current transformers, and in case you need to increase load capacity, you can use them. Okay. Next, think of it. Some design incorporate not current transformer, but so-called Rogowski coil. Maybe so it's measuring in equipment current sensors, like my finger in diameter and foldable. You need to put them around the wire. No? It's a current sensor. Like plastic pipe, you put them around the wire. Rogowski coil. Here should be wire. Rogowski coil. Rogowski coil don't have coil, it's coilless. And problem what Rogowski coil don't give you current. Rogowski coil give you first derivative of the current. To get current from Rogowski coil, you need to put an integrator on the path. Good thing about Rogowski coils, they are very linear. Bad thing, absolutely zero load capability. So without its protective device, Rogowski coil is useless. It cannot be used as a current transformer where you can plug, I don't know, ampere meter or multimeter. You can easily understand what you're dealing with Rogowski coil, coaxial output like on scopes, but it's two scopes has one. No, you're so typical, it's a BNC connector. Round with one central socket. Rogowski has a similar round connector, similar to BNC, but two sockets inside. It's very typical for Rogowski sensors. Rogowski coil gives out first derivative of the current, not the current. Usual metric, but here we have several dozens whole switchgears with Rogowski current sensors. Rogowski coil works only with relay it's intended for, because it needs an amplifier and integrating. Be careful with Rogowski coil, and they have zero load capability. One more thing you may find. I hate the one. Hall sensors. This is small for 250 amps. In reality, exists a larger version. It's a Hall sensor. Inside, coil, strange coil, and this key moment, Hall sensor itself. In physics, Hall effect. What's a Hall effect? If you have, let's say, block of semiconductor in the magnetic field and you apply an excitement voltage is 0, output will be some constant is 0 magnetic induction. Hall effect. Huh? From physics. Yes. Sensor based on Hall effect. Current. Can be is 0. Only need a source of E0. Looks very simple, yeah? Because induction in ring is proportional to current. Will not work. Hall sensors have a terrible zero shift on depends of temperature. When temperature changes, Hall sensor goes somewhere. This not working. Hall sensors do a good working model has a supplementary coil, amplifier powers the supplementary coil, and the signal goes to amplifier. It tries, this amplifier works to make the signal 0, compensating. Here it is, this IC with 2 transistors is an amplifier, and with the help of the supplementary coil, it tries to make Hall signal 0. In such case, it will be linear, as it can be, and will virtually have no zero drift, no zero offset. In reality, with the help of this thing, once a year at last, you need to check for zero offset and adjust it with this rheostat. Hall sensors often in protection of motors, comfort protection for motors, and in DC. Because such kind of sensor can work with DC current, with it offset. But mostly they appear as a current sensors for motor protection. More. Also, nowadays you can find field sensors, special antennas which can harvest H component of the electromagnetic fields, can be placed under the wire. No precision, but direction of fault they show. What else? What else with current sensors? Now you can buy so-called optical transformers. They are pseudo-optical and real optical current transformers. Pseudo-optical, high voltage line, 1 current transformer, 2 current transformer. This one goes to power converter. Also, I will show it schematically. battery, this to power ADC analog to digital converter should be load resistance, and then fiber optics. All this part is connected to line, it's under high voltage. With fiber optics ensures insulation on the ground. This has a ground potential. Very old version has digital to analog conversion. Now it's useless. Microprocessor controlling Ethernet. Simple Ethernet module, and outside goes what? Outside goes industrial network. Actually, it's the same Ethernet. Ethernet cable. Where are you? Ethernet and TCP/IP in it. Same thing on the industrial screen will be. There are today transformers. There are transformers with built-in digital interface and insulation with fiber optic loop. Also, good models produce what? Current samples with time stamps. They have built-in clock, support kind of NTP, network time protocol, and out will go set or flow, let's say flow, stream of time-stamped current values. But this is not true optical transformer. It's a good transformer for read ESC 61850. It's for digital substation, but actually it's a current transformer, only with good interface. Of course, there is no need for connection schematics, but it can be saturated. And it has error of this part, error core. It's powered by line current, but its error determined by core of this transformer. And there are true optical transformers. True optical. Fiber optics. Fiber optics use effect laser starring inside into coil of fiber optic cable. Outside goes also light, but angular shift between send and receive depends on magnetic induction of coils. If you need more, ask your Google for Pockels cells. Pockels cells. So with the help of Pockels cells, polarization angle of light is determined. These are true optical transformers. Superlinear, of course, they give out digital. They give the data for same timestamp with values. They are extremely expensive. Super precision, superlinearity, and absolutely monstrous price tag. Not for us. Okay, more. What's more? One more thing. Voltage. How can I get voltage? I can show coil. Here should be wire, and this small chip goes inside goes inside the slot is a Hall sensor. More, how can I get my voltage? When I need a voltage. Oh yeah, I know what I forgot. Yeah, I forgot one transformer. There is a special not very common type of transformer, I forgot of. Bus transformers used mostly for power plants for large generator outputs. Problem what? You have generator output transformer here 2, 4, 6 maybe kiloampere large current, but maybe something like it's cut off. Something like this. Inside copper buses. Insulators. Like this. Outer diameter more than meter. Like this. Problem. How to plan a earthfall protection. Problem with earthfall protection for generator. You cannot put a cable transformer there. It's really 3 pipes like this. One of the solutions is special cable bus transformer. Consists of 2 quite large. Wait 1 second. One frame and second frame. These frames are approximate, here can be 5 meters and here maybe 2 meters. Quite large steel frames. Through them bus I need to draw them. A, B, C. These are for kiloamp current. High current bus from generator go to this frame. Each frame has 2 windings. On each frame there are 2 windings. Maybe I will draw kind of primary side looks like something like this. Not visible, not visible, not. On secondary side, two windings. Oops. Okay, two windings connected in series and used for current relays. Green windings are connected in opposite and are powered from the auxiliary AC source. What's the idea? What's the idea of such strange design? See what the problem is. Here is magnetizing charge of a steel. At the very beginning, it's also non-linear. Maybe something like this. Such huge magnetic loops will seriously damage transformer precision because of non-linearity at a zero, at the starting point. To prevent it, working point is shifted artificially with the current of the green winding. There are two, each one is shifted on its own direction. But if they are equal, sum here, sum of induced by green winding will be zero. In reality, these are made adjustable. So balance can be set. They can be balanced. It's a very large. Okay, it will fit in this room, but it's a very large transformer. Mostly you can find it on power plants, output of generator. Transformer with double transformer to compensate non-linearity of the course at the very beginning of characteristic, offset current is applied. And to prevent influence from offset current to the earth fault relays, they are two and they compensating each other. Special transformer for bus bars. Yeah, now about voltage transformers. First, voltage transformers were very simple. A, B, C. At that time, so-called Aaron schematics was very popular. And this model, with Earth at B phase, without middle phase, was quite popular. The transformer, the voltage transformer. This type of design was very popular in early days. You can still find them. distribution network with two system matrix, voltage transformers also remain. These schematics, it's work for everything except Earth's fault protection. For Earth's fault protection, it's useless. Not good. Draw next one. But this schematic with two transformers on line voltage, you can find it. Useless for Earth's fault protection. For line to line, may be used. Next schematics. With, okay, I will save time. Okay. And full star connection. ABC voltage transformers. Most popular. Full star connection. 3 separate transformer, 110 kilovolts and higher. All will be equipped with separate transformers. No 3-phase blocks are produced. This thing is nice, but this is for phase voltages. Connection schematics, for example, grounded star 110,000 divided by square root of 3. Secondary voltage, also star, will be 100 volts square root of 3. In case phase voltage 57 volts. This is fine. Also, these transformers, it's industrial standard, are equipped with supplementary set of winding. What I will get from this? Open delta. What is here? Sum of A, B, and C voltage. And what's the meaning of this sum? What is silence? A phase plus B phase plus C phase. And 0, maybe not 0, but it will be triple 0 sequence voltage. Yes, 0 is a good term here. It's voltage for your Earth's fault protection. They always produce, they always are rated for 100 volts. In case of Earth's fault, you will get 100 volts there. Open triangle, open delta, call it as you wish, but it's a winding for 0 sequence voltage. Analog transformer give 0 sequence voltage. Digitals do not. It's your problem, calculate by yourself. 0 sequence for your Earth's fault protection. voltage networks can use separate transformer for each phase or one transformer for all phase, but special kind of transformer. Special. You cannot use ordinary free leg transformer as a current sensor. You need a special not every design is suitable here. Okay. This will be AB. Yeah. A, B, C. Ground. Primary side. Is a grounded diode. This transformer is for isolated neutral networks, but anyway, it's a grounded diode. Secondary side will have two windings. A. B. Sorry, it's not A. It's a C phase. This one A, F. Connection. M, A, B, C. Watch this moment. Many transformers for distribution network, they mimic all the schematic with grounded B phase. And they have ground point not at the end, but at the B. Remember this. Voltage transformers for distribution networks many years were produced with grounded B phase, not center of the star. To mimic olden version of two transformer on linear voltage. Don't be surprised. If this network, this part is for nominal voltage 10 kilovolts, this one will always be for 100 volts. But that's not all. All these transformers do have additional winding. Do have additional maybe like this. U0. They have triple U0 winding with nominal voltage 100 volt. In case of Ohm's fault, voltage at this winding will be 100 volts. All these old school barrel transformers do have additional winding for zero sequence voltage. And now question, Why such strange design of 5 legs? You see what I draw a 5-leg core? These additional legs are for 0 sequence. Standard 3-leg transformers like this are not suitable because there is no way how the 0 sequence current may be closed. They will have near 0 resistance in 0 sequence circuit and will burn and blow in case of earth fault. To prevent it, path for 0 sequence magnetic flux should be 4-leg is good, but 5-leg transformer. They have a side legs for 0 sequence or completely enclosed design where auxiliary design windings are enclosed in frames. It's one common barrel, but inside for each winding is a complete enclosement of steel. It's not a cheapest thing in the world. That's why typically such transformer will be only on Bausbach side. Line voltages are taken with simpler thing. This thing is precise, so for metering it should be installed. But very typical design, you have 2 busbar systems with interconnected switch, 14 kilovolts for example, and 2 voltage transformer for each of the busbar systems. Other voltages, line voltages, are taken with capacitive divider. 1 second, I will draw it. Idea of divider: C1, C2, ground, discharge, 1 or 2. So, if X1 is on C1, Xc2 1 divided by omega C2. Second voltage can be written as U1 X2 divided by Xc1 Xc2. Here how capacitive divider works. Next time, at the first floor near the green ball, you saw 10 kilovolt switch. Look closer on insulators from the back side. Strange insulator with coaxial wires going out of them. When the buses are connected, they are quite strange insulators. They are capacitive dividers. These things are not precise. They capacitance is quite significant, dependent from the outer temperature. But to detect there is voltage or no, it's enough. And for our case, voltage direction. They are not precise, but much cheaper than transformer. So on line connection in middle voltage dividers. Looks like insulator with coaxial wire going out of it. Also, you may find like this size for 10-11 kilovolts were quite popular. This size, strange unit, looks like current transformer, but no current terminals, and outside goes coaxial wire. Combined sensor. inside brown epoxy resin like this transformer outer shell. Inside a capacitive divider and Rogowski coil. Combined current voltage sensor with this size. Looks like strange current transformer, but it's coaxial output. Rogowski coil and capacitive divider. In theory, exists optical version. Exists. Never saw in person because it's extremely expensive thing. But there, for super high voltage, optical voltage, they are not transformers, do exist. What else? Very rare thing, DC transformers, DC current transformers. You think, can DC transformer exist? It's nonsense, it's against physics. Do exist. Current transformers for DC lines. Idea uses saturation. The idea thin frame, this is DC line, has two coils. Not this, but this way. Coil A is powered from auxiliary transformer, and coil B goes to comparison device. It also has additional sensor. Idea, again, usage of saturation curve. Without DC component, you would be somewhere here. And current from auxiliary, from this coil transforms to this coil without any disturbance. The high is plus DC. See what happens? Work area goes into saturation zone, and current, send current, will be disturbed and will not go to receiving coil completely. No, it will be equipped because of saturation. If magnetic material is selected well, you will have area which it's not linear, it's linear, depends of how to say transformer ratio decay from the DC current. Idea is what this coil is saturatable, and the higher is DC current, the deeper is saturation, and less current will be transformed from sending coil to receiving. That's how DC transformer works. They use still saturation effect. Select saturated area with well-defined slope, and it works. X Supra. Hi, are you teacher? Yes, I'm a teacher. You may also how to say, put a hypothesis what I'm a guy from Mars or outside space, but I'm paid as a teacher. Yeah, saturatable transformer uses effect DC sensor. User would use fact that steel cores are saturatable. What else? What I forgot? Special kind of sensors for they are used at the output of inverters. Thermal sensors contains heating element and thermal sensor. They measure current by thermal effect of it. Usually, not a very popular thing in power energetics, but they are to measure a true effective or RMS value, current value from excitement inverters. Usually it's a problem. Excitement system of generators, they look nice, in theory. We supply direct current to rotor and we got induced voltage in stator. In reality, they do kind of slow voltage. Current is not so disturbed, but voltage of exciters is something. BTV 3000 volts. No, some have 600 volts and 3000 amps. What a nice to measure, 3000 amps. Because of the non-sinusoidality, sometimes thermal converters may be used. What else? What kind of sensor I forgot? Okay, main transformers we have. Yeah. One more current transformer. You come here. Oh, take a look at this transformer. Yeah. See? Primary winding. Very massive. It's for high current. Secondary, much thinner, but watch at core. See? Only half of steel. It's a saturatable transformer. One of the versions how it can be created. For example, you can drill a set of holes. This is transformer with saturation zone. These are zones of saturation. Why it's needed? This is current limiting transformer. It's used sometimes in earth fault protection to prevent burnout of sensitive relays. Here goes ER plus B plus C. This one ensures what in case of small currents relay operates, but in case of double earth fault, we will speak about it. This will limit current through relay. It's a special current limiting transformer used. It's for high currents. It should withstand 200 amps. This winding. This thing is for sensitive relay. It's an interim special saturatable transformer. In case of low current, this area, where only half of steel, works as usual. And on small current, it's a simple transformer. At high current, this area saturates and secondary current will be limited. Current limiting transformer for earth fault protection. Okay, I'm afraid I spent all my time today. Questions online? Maybe some question. Yeah, I know what you are waiting for. Let me in. Let me in. Let me in. Okay, šodien mums ir pirmdiena. Can I open this one? Slow. Oh. Nice. Take a look. NFC read successful. Impossible. And what about this one? Come here. Come here. Come here. I see no questions here.